This presentation will cover today's second case study. This case study is on the Bow River Bioengineering Demonstration and Education Project. For this presentation, I'll have a co-presenter who's Jack Dietz, who will present on the construction component of the project. Jack is an EIT at KWL now, but before becoming an engineer, he worked as a laborer for the contractor who built the BDEP site, so very much has hands-on experience building the bioengineering approaches at the BDEP site. What I'd like to cover with you in this presentation are the BDEP project planning, design, construction summary, monitoring results, and education initiatives. After this presentation, there will be a 15-minute period where questions can be asked to anyone on today's panel. So as I mentioned in part one of today's workshop, there has been a resurgence in the use of bioengineering techniques since the 1990s. In Calgary, there was a large spike in the use of bioengineering approaches after the 2013 floods, with approximately 12 green bank and repairing projects prior to 2013 and a large number afterwards, as you can see from the chart. Now that bioengineering was becoming more popular, a key question arose: were bioengineering projects in Calgary meeting their objectives? Southern Alberta's unique climate, the low precipitation, harsh winters, and Chinooks means that practices from other regions may not work as well here. Observations from Alberta Environment and Protected Areas and the City of Calgary showed variable success, particularly with vegetation. While some sites thrived, others struggled. This led to the decision to launch a demonstration project to improve bioengineering project success in Calgary and in southern Alberta, as failures were discouraging broader use despite the technique's potential benefits. So the provincial government, Department of Environment and Protected Areas, and the City of Calgary collaborated to develop the BDEP, which is made up of three components. One, the design and construction of a bioengineering demonstration project on the Bow River. Two, a 10-year post-construction monitoring program. And three, education programming. The design and construction component was administered by Alberta Environment and Protected Areas through the Southern Alberta Fisheries Habitat Enhancement and Sustainability, or FISHES program, and the monitoring and education components are both administered by the City of Calgary. There are several objectives for the project as listed here: to stabilize slopes and control erosion, re-establish fish habitat degraded by recent flood protection activities using bioengineering techniques, restore riparian health and related functions to improve watershed resiliency, demonstrate a range of bioengineering techniques and their applicability to different site conditions, create a more aesthetically pleasing river interface, increase awareness and understanding of bioengineering, and facilitate knowledge transfer, research, and partnerships between the City of Calgary, the province, professional practitioners, industry, academia, and the public. And finally, to monitor, evaluate, and report on the overall effectiveness and cost of the project. The BDEP site has a rich history that reflects the evolution of both the Inglewood community and Calgary. Aerial photos from 1952, 1981, and 2015 on the slide here show key changes over time. First, the site once featured an old bridge crossing, later replaced in 1981 by a larger one. Remnants of the old bridge piers and abutment are still visible today, as you can see in the 2015 aerial. Second, the Grand Trunk Pacific Railway line ran through the site from 1912 to the 1970s, and its embankments remain visible. The former Inglewood refinery that was operated from 1936 to 1973 and later asphalt plant left a legacy of contamination with ongoing remediation efforts. Finally, the BDEP site is home to one of the deepest scour holes in the Bow River, which deepened by 4 meters during the 2013 flood, when the riverbank also receded by up to 40 meters. The BDEP, as mentioned, is located in the historic Inglewood community in Calgary, covering 720 meters of the Bow River's right bank, from 80 meters upstream of Cushing Bridge to 640 meters downstream. It includes 3 sites: Site 1, Site 2, and Site 4, with several subsites. There is no Site 3 or 5 due to budget constraints. In total, there are 10 bioengineering treatment areas where 14 techniques were used to address various site conditions, of which 7 are new to Calgary and 7 are techniques that are typically used. Designs were completed between July 2016 and September 2017. Construction took place from February 2018 to June 2019. Education programming began in 2018 and monitoring will continue through 2028. Now getting into the BDEP sites and the bioengineering treatments that we used. Site 1 is shown in the aerial photo here. Site 1 is exposed to moderately severe hydraulic conditions, including the scour hole that I mentioned previously. so the designs reflect the need to protect against tow scour and high velocity flow from under the bridge. The site is about 370 meters long and was divided into 4 treatment areas. A key feature of Site 1 is the wildlife passage corridor that we included along the terrace, under the bridge, and back to the riparian zone. The sightlines were important under the bridges, so the most upstream bioengineering technique was a vegetated gravel bar using rooted live cuttings that was used to support this. There was no bioengineering under the bridge. Then a conventional timber crib wall and a timber crib wall with fish shelters was included, both with soil wraps above. Then a section of brush mattress with contour fascines and brush layers was included. Riparian planting was above the bank. Amphitheater for education activities is located along the wildlife corridor in the middle of the site. Site 2 is a bit more protected from erosive forces since it lies between 2 existing rock groins. Here we piloted purely vegetative bioengineering techniques, so no rock, concrete, or synthetic materials were used. Of note at the site is that there is an existing bank swallow colony that nests in the scarp along the upstream half of Site 2. Instead of disturbing the colony, we constructed a box or tow fascine along the toe of the site to provide vegetation at the water's edge and erosion protection. Then we regraded the bank on the downstream section and tested 3 different treatments above the box fascine, including a brush mattress with contour fascines, hedge brush layers, live staking, and riparian planting. There is also a gathering space for education activities at the upstream end of the site. The box fascine and hedge brush layers are the first known use of these techniques in Calgary. At Site 4, we trialed 3 methods to vegetate existing riprap erosion protection. The existing riprap was placed in 2013 to 2014 to protect critical infrastructure and rebuild the road as part of the 2013 flood mitigation efforts. At the upstream site, we covered the existing riprap with soil, planted container plants, seeded the topsoil with native grasses, and covered it with erosion control matting. In the middle site and downstream site, the riprap voids were filled with topsoil and planted with different plant stock, then seeded with native grasses. In the middle site, we used plugs, and in the downstream site, we used live cuttings. Construction of the project took place from February 2018 to June 2019. The contract was tendered using a modified tender that included evaluation of contractor experience and project understanding, as well as price. There was about 13,000 cubic meters of material moved, mostly to make way for the wildlife corridor on the lower terrace above the crib wall. There was about 3,700 cubic meters of rock placed, mostly at Site 1, to provide tow protection against high velocity flow. About 30,000 live cuttings, 2,300 potted plants, and 100 trees were installed, and about 2,000 tons of concrete, steel, and wood debris removed. Now, Jack will discuss his perspective on constructing the bioengineering techniques at each of the sites.
Thank you, Mike. Over the next few slides, I will discuss some construction details of the bioengineering demonstration and education project, which I had the pleasure of being involved in, including issues and resolutions that may be helpful in future delivery of bioengineering projects. As mentioned earlier, the vegetated riprap component of this project was constructed in summer using live-rooted cuttings rather than dormant cuttings. It made for a slow-going process. However, the resulting high survivability and natural-looking plant distribution were worth the hassle. To install the timber crib wall, an in-stream isolation barrier was constructed prior to the start of the aquatic restricted activity period. The barrier effectively mitigated against large turbidity plumes until a late freshet swell in the Bow River caused it to overtop. This unfortunately required the placement of hundreds of additional sandbags along its crown. Boulders were placed as a fish habitat promoting base for the crib wall. Due to the high water levels, reflective flags were installed in the top of each boulder so their position could be seen when submerged and the wall placed correctly on top of them. The cedar crib wall was built in sections at the top of the bank. Once complete, each section was lifted and secured in position at the toe of the bank via slings and a pair of large excavators. In the soil wraps, it is crucial that the core matting is placed overlapping from upstream to downstream on the exposed face. This requires overlapping it the opposite way before folding it over the soil. Skilled excavator operators ensure that the matting was sufficiently tight over the exposed face of the soil. It was finicky at first, but once the technique was learned, it progressed quickly. Site 1-4 ended up being double hydroseeded due to a perceived failure of the first attempt. After the second attempt, grasses in the area began to sprout with a vengeance, which is a good reminder that native species can take longer to establish and to trust the process. Prior to any work in Site 2, a length of bank swallow habitat was covered in non-woven geotextile to avoid disturbing the birds. The birds thankfully did not return during construction. The tofa sheen was backfilled using pea gravel, which washed out en masse during high flows prior to root establishment. The plants along the bottom and toward the slope tended to have higher survival rate than those exposed toward the front. Initially, a proportion of the fascine plants were intended to be a filler species, but it actually ended up being more cost-effective to just use dormant cuttings for the whole thing. The brush mattress was initially buried too deep and subsequently uncovered to a very minimal burial depth as pictured, which resulted in very high shoot density. Hedge brush layers, similar to soil wraps, were tedious to learn, but progressed quite efficiently once we did. One row at a time from bottom to top, excavation was completed, plants and soil amendment were placed, and then the excavation for the layer above was used to backfill, and so on. A hammer drill was used to create pilot holes for the live stakes. The stakes were inserted by hand, and when necessary, rubber mallets were used to pound them in. Damaged tips were treated, but some stakes sustained damage that was undetected until they failed to produce shoots. There are other methods to create pilot holes, but the key thing is to minimize pounding on the stakes themselves. In Site 4, it was initially proposed to void fill the riprap with a material slurry, but this was rejected due to the risk of creating turbid plumes. Only dry topsoil and pit run were installed, and no turbidity spikes were observed. Topsoil and pit run were placed from the nearby road using a telebelt and vibrated into the voids using a plate tamper. The plugs in Site 4-2 had a quite high survival rate due to their roots being fully surrounded in topsoil. For Site 4-3, however, dormant cuttings were not installed until the fall. It proved difficult to guess correctly where the deep voids between rocks might be, and a hammer drill was used to create pilot holes for the stakes. This was effective intermittently at best, with some stakes being placed with their root tip in the middle of a rock. Best practice would be to install willows first and void fill afterward. Mike will now continue with the post-construction aspects of the project.
Thanks, Jack. For the post-construction monitoring component of the project, the objectives are to show how the project and bioengineering techniques improve fish habitat, wildlife habitat, riparian health, and bank structural integrity compared to a conventional riprap approach. The site is being monitored over a 10-year period starting in 2019, which was year 1 post-construction, then year 2, year 3, year 5, and year 10 post-construction, where we finished up to year 5 monitoring. The site is being monitored under the City of Calgary Riparian Monitoring Program, which you've heard lots about this morning. Here are some photos of Site 1 to show the progression from existing conditions to year 1, year 2, year 3, and year 5 post-construction. The first photo shows the original condition of the bank, where you can see the exposed concrete rubble. The other photos show the growth of the brush mattress, contour fascines, and brush layers in the foreground. In comparison to the original condition, there is now overhanging vegetation that enhances fish habitat by providing shade, cover, food, and nutrient inputs, and a greater than 30% improvement in riparian health and woody canopy cover that is over 90% in the bank area. Here are some photos of Site 2, again to show the progression from existing conditions to year 1, year 2, year 3, and year 5 post-construction. The photo on the left shows the original conditions, where there is an almost bare riverbank with no cover or riparian vegetation. The other photos show the growth of the live staking in the foreground and the hedge brush layers in the background. The woody canopy cover ranges between 70% to 100% in the bank area at Site 2. Now here are some photos of Site 4, again to show the progression from existing conditions to year 1, year 2, year 3, and year 5 post-construction. The first photo on the left shows the original conditions of the site with the exposed riprap bench along the river. The other photos show the growth of the void-filled riprap with topsoil and shrub plugs. We have extensive data from the monitoring assessments over 2019 to 2023, but for today, I'll provide a summary. For more details, feel free to contact me or download the full report from calgary.ca/BDEP. Key findings include no erosion, scour, or displacement issues. Materials are in good condition. Fish were observed using the shelters, boulders, and surrounding habitats. Birds were observed using the enhanced riparian habitat. Large mammals such as deer and coyotes were documented in the wildlife corridor. Riparian health improved by 5 to 25% across all sites. Year 1 vegetation survival was 80% and met the contractual target. Woody canopy cover increased from 31% in 2021 to 60% in 2023, in part due to extensive balsam poplar suckering at Site 1. BDEP is providing better wildlife and fish habitat, wildlife passage, and riparian health than a conventional riprap site, with a approximately $1 million cost savings. Because of the available database for plant growth data from the Riparian Monitoring Program, We can compare the BDEP monitoring data to see how vegetation is establishing against expected values. These box plots show leader growth on the left and shoot length on the right for year 1, year 3, and year 5 age classes. The line in the middle of the box plot is the median value, the bottom of the box is the 25th percentile, and the top of the box is the 75th percentile. The lower end of the whisker is the statistical minimum, and the top of the whisker is the statistical maximum. The data points above the whiskers are outliers. Now, the overall average leader growth and shoot length for live cuttings in each BDEP site are plotted on the box plots in the circles there. Most of the sites plot between the median and the 75th percentile for growth, which shows overall success at BDEP. However, Site 4 in is between the 25th percentile and the median in year 1 for leader growth and year 3 for shoot length, and below the 25th percentile for shoot length in year 1. These trends were noted, and remedial planting occurred in year 2 and year 3 post-construction, so the results in year 5 are much more in line with expectations. Now looking at some more detailed results for canopy cover. The first chart is the woody canopy cover for the live cuttings by subsite, which roughly corresponds to bank treatments or bioengineering treatments. In short, most of the techniques are meeting or exceeding the cover target from the literature of 66% for each of year 1, year 3, and year 5 post-construction, except for 2 sites where we know that there has been establishment issues at the vegetated riprap gravel bar on Site 1-1 and the void field riprap with live staking at Site 4-3. The second result is the woody canopy cover for potted plants by subsite. Again, that corresponds to the top of bank or repair and restoration areas. Cover in these areas of the site is not meeting the targets, except for in areas where balsam poplar suckering was occurring at Site 1 in year 5. This is the main reason for the lower than expected cover across the entire project, and is mostly related to low planting density, but also competition from herbaceous species that was limiting growth. This was identified in year 1 and year 2 monitoring and addressed via the maintenance program, with resulting increases in woody cover observable in year 5 at many sites. We have had considerable interest in the riprap retrofit techniques at Site 4. To further the case for why it is important to vegetate bare riprap, we did a transect on the control portion of the site in 2023 downstream from our treatment areas and found no vegetation after about 10 years since construction. So that area is shown on the right side of the photo here. Because of the risk for bare riprap of getting colonized by invasive species, we think it's better to plant what you want versus get what you don't want. Based on the monitoring results for Site 4, it seems that the best technique for vegetating existing riprap is void filling with topsoil and planting plugs. We caution the use of topsoil, however, in higher exposure locations, particularly since it's highly erodible. I'd suggest using something like a dirty gravel or what we'd call pit run, or maybe river gravels instead. Several education initiatives are underway, including the installation of interpretive signage and the amphitheater and gathering spaces already installed at the site. We've delivered several technical presentations at several conferences and workshops. We've given technical tours of the site to students and city staff. The award-winning Riverwatch program that educates thousands of students about bioengineering as they pass the site, and then we've contributed to the script that they use in their discussion. Additionally, we're collaborating with the University of Calgary on research to monitor soil moisture in the riverbank to enhance irrigation and plant growth. At this point, I'd like to acknowledge the project team shown here. The project co-owners were the City of Calgary and the Alberta Environment and Protected Areas. The prime consultant, environmental and education lead was at the time Himer EnviroChem and now Ausenco. KWL was the design lead. O2 Planning and Design was the landscape architect. Terra Erosion Control and Polster Environmental Services were the bioengineering specialists. Thurber Engineering were the geotechnical engineering consultants, and Riverwatch supported the education component. TFH Enterprises were the prime contractors. So now we have about 15 minutes for questions and discussion. Thank you.